Hi there and welcome to Hegarty Maths. It's Mr. Arnold here, and in this video we're going to take a look at the first video on differentiation. It is mostly geared towards A-level maths, but is applicable to most other maths modules, so hopefully you find it useful. Okay, now in previous videos we've discussed the idea of gradients of straight lines. So if we had a straight line such as this, with a y-intercept here at the point C, 0C should I say, 0C. The equation of this line is y equals mx plus c. The gradient is the value m, and that tells us how far up you go with relation to 1 unit across. So if I go across 1 unit, I would go up m units, or sometimes if it's going down, for every unit across, for every 1 unit in a positive x direction, I might go m units down. So that's all about straight lines, and that's fairly straightforward. But differentiation looks at finding equations or gradients of tangents to a curve, such as this. So suppose we have a function that's a curve like so, and I wanted to know, well, what is the rate of change of the curve at that particular value here? What we would look for is something called the gradient function. And the gradient function allows us to find the gradient of that tangent to the curve at that particular point there. Now, I'm not going to go into the details of how this is derived from first principles. Mr. Hegarty actually does it particularly well in his other videos, so do check that out. I'll mainly focus on applying these rules. So just to kind of show you and demonstrate what Mr. Hegarty talks about in his video, I'm going to go to one of my favourite websites, desmos.com, and I will show you some curve here. Now, don't get scared or frightened by this information over here on the left hand side. The video is not based around that. I just want you to demonstrate. I want to demonstrate what's going on. So if we have a curve such as this, and I have a point on the curve. Now, the point on the curve can move, and if I want to find the rate of change of the curve at a particular point, or at this particular point, I need to find the gradient of the tangent. I need to find the tangent to the curve at that point. So there's the tangent there at that point. Now, I don't want to have to draw this straight line in, because I may not get it as accurately as possible. And I don't want to be kind of counting squares, how far across and how far up. So what differentiation and calculus does, it gives us another point, it takes another point on the curve, and it forms a chord. And you'll notice that if I make the difference between this point here and this point here, if I make them small, if I make them closer and closer and closer and closer together, this chord here becomes a very accurate estimate for this tangent. So just once again, if I pick 2 points on the curve, and if I was to work out the gradient of the line between those curves using coordinate geometry, that would give me the equation of a line, or the gradient of a line. I can work out the gradient of this line here between these 2 points. But if I make this chord smaller and smaller and smaller and smaller, the gradient of this line, this chord here in red, is getting closer and closer and closer to the gradient of the tangent. And that is the process of calculus, and what calculus and differentiation in particular, should I say, does. Now, as I said, I'm not going to derive these from first principles. Do check out the other video if you want to see how that works. What I'm going to do is focus on the rules of differentiation, the first few rules, notably differentiating polynomials. So, if we have a polynomial, y equals a times x, and that's the function, and we take the derivative, the function y, the derivative of y is dy by dx, and essentially what's happening is we're taking the power down in front, we're multiplying by the coefficient of x, and we're reducing the power by 1. Similarly, if the function is given in function notation f of x, and it's ax to the power n, so some polynomial of degree n, the derivative of that, sometimes called f dash x or even f prime x, again, same idea, the power comes down in front, so we take the power down in front, we multiply by the coefficient of x, which is a in this case, and we reduce the power by 1. So formulas can look a little bit complicated at first. Let's see the process in action. So let's take a look at example 1. I've got a few questions here for us to practice. I want to differentiate with respect to x. So if I have x squared, the derivative d by dx, the derivative with respect to x of x squared is going to be equal to, so we take the power down in front, we multiply by the coefficient of x, which is 1, so 2 times 1 is 2, and we reduce the power of x by 1, which is going to be 1. Now, mathematicians are lazy, so I'm going to leave out that 1. So the derivative of x squared is 2x. So I'm going to take the derivative of the second one here. So I want the derivative with respect to x of 4x squared. Same idea again. Power comes down in front and we multiply by the coefficient of x. So 2 times 4 is 8. Reduce the power by 1, which gives me just x. So x squared becomes x. The next one here. The derivative of 3 with respect to x, d by dx of a constant 3, a little bit of thought, must be equal to 0. The derivative of a constant is always 0, because if you imagine a graph, and suppose we had the value 3, let's put y equals 3 in. So say this is 3, and we have a straight line coming through here. I'll change the colour in a moment. So that's y equals 3. Well, the derivative or the gradient of that line is 0. It's a straight line. It doesn't go up, it doesn't go down. It's a constant. So the derivative or the gradient of that line is 0. So when we take the derivative, we're finding the gradient function of the tangent to the curve. Alright, next example here. So I want the derivative with respect to x, d by dx, of 8x to the negative 2. So again, applying the rule, the power comes down in front, which is negative 2, multiplied by the coefficient of x squared. So I'll do this a little bit longer. So I'm doing negative 2 multiplied by the coefficient of x, and we reduce the power of x by 1. Don't make the mistake of writing negative 1 here. It's going down by 1. I've got to take 1 away from negative 2, which is negative 3, which means we get negative 16x to the power of negative 3. And the final example here, d by dx of x to the negative 3. Again, power comes down in front, multiply by the coefficient of x, which is 1 in this case, so we get negative 3, and reduce that power of x by 1, we get negative 4. Alright, let's take a look at a few more examples. So I need to find the derivative of y equals x to the power of 5 plus x squared. Now, just so you know, the derivative d by dx of the sum or difference, d by dx of the sum or difference of 2 or more functions. So if I'm taking derivative of the sum or difference of a couple of functions, that's simply equal to the derivative d by dx of f of x, the derivative of f of x plus or minus the derivative of g of x. In other words, take the derivative of each function individually and just add them together. So if y equals x to the power of 5 plus x squared, that means dy dx. I'm using dy dx now because it's given in terms of y. Dy dx will equal the derivative of x to the power 5, which is 5x to the power 4. So power down in front, multiply by the coefficient of x, and then reduce the power by 1, plus the derivative of x squared. So power comes down in front, which is a 2, multiply by the coefficient of x, which is 1, and reduce that power of x by 1, so 2x. Let's have a look at the next example. So y equals 6x cubed plus 5x to the negative 2 dy by dx. Again, power comes down in front, multiplied by the coefficient of x. So 3 times 6 is 18x. Reduce that power of x by 1, we get 2. Power comes down in front here, which is going to give me negative 10. So I'm adding negative 10, which is just negative 10x, and reduce that power of x by 1, negative 3. And then finally, y equals x squared, subtract 4x plus 1. So dy by dx equals, power comes down in front, reduce that power of x by 1, so we get 2x. Subtract 4x, the power here is 1, so I'm taking the power down in front. 1 times negative 4 is negative 4. And when I take x to the power 1 and I reduce it by 1, I get x to the power 0, which is 1. And then finally we have the derivative of 1 is 0. So the derivative of a constant is 0. I just want to show this one again just over here because we didn't do any examples such as that. So we have negative 4x. I'm taking d by dx of it. Remembering. Okay, so this is the power 1. So I do 1 times the negative 4. 1 times the negative 4. And we're multiplying that by x to the power 0. 1 times negative 4 is negative 4. And anything to the power of 0 is 1. So I'm doing negative 4 times 1, which is simply just negative 4. One more. So y equals 4x cubed plus 3x to the negative 4. So dy by dx equals, take the power, multiply by the coefficient of x squared, or of x, beg your pardon. So we get 12, reduce that power by 1, x squared, power multiplied by the coefficient of x, so negative 4 times 3 is negative 12, reduce that power by 1, x to the power of negative 5, not negative 3. We're reducing it by 1. It's going down by 1. And that's the derivative taken there. So that's just the process of differentiating polynomials. Let's look at a little bit more application of it. So I want to find the gradient of the curve at the point given. So I'm going to find the gradient of the curve at this point given, or the gradient of the tangent to the curve, if you like. So I've got y equals 3x squared plus x subtract 5, and the point given is 1 minus 1. To find the gradient of the curve, I need to find the gradient function. So let's get dy by dx. So dy by dx will equal, take the power, multiply by the coefficient, reduce the power by 1. Do the same here. The power is 1, the coefficient is 1, 1 times 1 is 1, and x, when I reduce that power by 1, I'm going to get a 0 here. X to the power 0 is 1. So the derivative of x is simply just 1, and the derivative of a constant is 0. So the gradient function is 6x plus 1, and I want to find the gradient of the curve at this point. So what I'm going to use is, I'm going to use the fact that x has a value of 1 here. So what I'm doing now is, I'm going to take dy by dx, and I'm going to evaluate it when x is equal to 1. So I substitute 6 times 1 and add 1, which is going to be 7. Now I just want to demonstrate this one using my favorite tool, Desmos, and show you exactly this. So we had 3x squared plus x subtract 5. Let's go to this one. So f of x or y equals 3x squared subtract x, plus x subtract 5 plus x subtract 5. And let's just zoom out a little bit here. So you can see, and let's change the color of this. So the function given, f of x, is clearly a quadratic. It's a parabola. The gradient function, when we worked it out, you might notice is a linear function, 6x plus 1. And if we go back to Desmos, there it is. There's the gradient function here. Now, let's see what the value of the gradient function is when x is 1. We should get a value of 7. Let's check and see. So when x is 1, when x is 1, let's see what the gradient function has a value of. When x is 1, y is 7. So the gradient of the tangent to the curve at that point 1 is 7. And if we go back to Desmos, so the gradient of the tangent to the curve at 1 is 7. Okay, let's have a look at another example. So I need to find the gradient of the curve at the point given, and I've got y equals x times 2x subtract 3, and the point given is 2, 2. Now this is not particularly friendly. There is another rule which is we could use here, but the quickest way to tackle this is to simply expand it out first. So x times 2x is 2x squared, x times negative 3, negative 3x. So that's y. Find a gradient function, dy by dx. And then let's sort this out. So 2 times the 2 gives me 4. Reduce that power of x by 1. 1 here, 1 which is here, times the negative 3 is negative 3. And reducing that x, the power of x by 1, gives me a 0. And anything to the power of 0 is 1. So negative 3 times 1 is negative 3. Okay, we're evaluating now at the point given. So where x is equal to 2. That's what we're going to do. We're going to evaluate. So dy by dx. And we're going to evaluate that where x is equal to 2. Equals 4 times 2 subtract 3. 4 times 2 is 8. 8 take away 3 is 5. Okay, excellent. Well, another question. I want to find the gradient of the curve at the point given. So, same idea again. Find the gradient function, dy by dx. The gradient function, dy by dx, will be equal to, power comes down in front, multiplied by the coefficient, which is going to be 2. Reduce that power by 1. And then, same idea again, power comes down in front. So negative 1 times negative 2 is positive 2. Reduce that power by 1 gives me negative 2. So that's the gradient function. And what I need to do now is I need to evaluate it. I need to evaluate it when x equals 2. So we're going to do dy by dx. We're going to evaluate when x is equal to 2. So substitute in 2 times 2 plus 2 by 2 to the power of negative 2. 2 times 2 is 4 plus 2 times 2 to the negative 2. Well, that's just the same as 2, and I'm going to use the laws of indices. So anything to a negative power is 1 over that power. So we end up with this. 4 plus, and 2 over 2 squared is simply 1 over 2. So 4 plus a half is equal to 4 and a half. 4 and a half, not a quarter. I don't know why I've written that down. 4 and a half. Okay, next example. Find the equation of the tangent to the curve at the point given. So I'm going to find the equation of the tangent to the curve at the point given. Okay, so similar idea again. In order to find the equation, a tangent, by the way, equation and a tangent. A tangent is a straight line. So we're going to use coordinate geometry, and the equation of any straight line, we're going to use the gradient and the point. Gradient point method. I've done that in a recent video, so it should be fresh in our minds. X1 and Y1. So I need to find the gradient at this particular point, and then I'm going to use this point and use the gradient point method from coordinate geometry. So in order to get the gradient at this particular point, I need to use the gradient function dy by dx, and that's going to equal power multiplied by the coefficient, drop the power by 1. Again, the power is 1, multiplied by -6 is -6, drop that power by 1, we get a 0, x to the power 0 is 1, and the derivative of a constant is 0. So we got 4x subtract 6, that's the gradient function. So what I need to do now is I need to evaluate dy by dx, and I'm going to evaluate it when x is equal to 1. I'm evaluating the gradient function at that particular point. So when x is equal to 1, and we get 4 times 1 subtract 6, which is going to equal -2. So the gradient is -2. So the gradient at that particular place is -2, and the point we're dealing with is 1, 4. So we're going to use y minus y1 equals m times x minus x1. Points are labelled, hopefully. x1, y1. Okay, so we get y minus 4 equals m, which is -2, times x minus x1, which is 1. So we get y minus 4 equals, expand this out, minus 2x plus 2. And then finally, I'm going to write it in the form y equals mx plus c. Adding 4 to both sides, we get this. Y equals -2x plus 6. Now let's see how well we did here. So we had 2x squared subtract 6x plus 8. 2x squared subtract 6x, and I think it was plus 8. Yep. Plus 8. So there, there is the function, 2x squared subtract 6x plus 8. And I want to see if the gradient of the tangent to the curve at 1, 4 is y equals -2x plus 6. Let's try that. Y equals -2x plus 6. So y equals -2x plus 6. So when x equals 1, you can see it here. Zooming in. When x equals 1, lo and behold, that looks like a tangent. So the equation of the tangent to the curve when x equals 1 is -2x plus 6. Spot on. Alright, one more. Now you may want to pause the video and try this. Okie doke. So I need to find the equation of the tangent to the curve at the point given. This time we've got a square root. Now calculus or differentiation doesn't tend to handle this type of square root particularly well, so I'm going to write it in index form. Make life a little bit easier. And this is going to be 3x to the power of a half. So it is very important. It is very important that you remember your laws of indices for this. Alright, so once again, let's go for the gradient function. If I want the equation of the tangent, I need the gradient function. So dy by dx will equal the derivative of x is 1, because the power is 1. I multiply by 1, I get 1. Drop the power to a 0. X to the power of 0 is 1. So 1 times 1 times 1, which is 1. Power comes down in front, so negative 3 times by a half, I'm going to write as negative 3 over 2. And when I reduce the power of a half by 1, I get x to the power of negative 1 half. The reason, because a half subtract 1 equals negative 1 half. Right, now I need to do is I need to evaluate this when x equals 4. So I need to evaluate dy by dx when x equals 4. So substitute in, we get 1 subtract 3 over 2 times 4 to the power of negative 1 half. Which equals 1 subtract 3 over 2 times by, well, 4 to the negative half equals 1 over 4 to the power of a half, which equals 1 subtract 3 over 2 times by, and 4 to the power of a half is 2. So we get 1 subtract 3 over 4, which equals 1/4. So the gradient is a quarter at that particular point. This is a gradient function. The gradient function allows me to find a particular gradient at a particular value of x. In this case, x equals 4. So the gradient at that point is a quarter. So I'm going to use we're going to use y minus y1 equals m times x minus x1. Remembering, equation of a tangent is the equation of a straight line, so you need the gradient and you need a point. We have the point, we also have the gradient. So we get y minus y1, so y plus 2 in this case, equals m, the gradient that we've just worked out, which is a quarter, times by x minus x1, so minus 4. And now let's tidy this up. Y plus 2 equals a quarter x subtract 1. So y equals, subtracting 2 from both sides, a quarter x subtract 3. And that's the equation of the tangent to the curve at the point given. Okay, that's it for this video. Hopefully you found it useful. I'll be back again with another video soon. All the best and take it easy.